So for this second talk of the morning, we've got the pleasure to have Christophe Garban from Lyon, and he'll talk about the backbone.
Thank you very much for this invitation, and thank you very much to organize a conference in honor of Greg. Today especially there are many former PhD students of Greg and postdocs also. So I guess I'm not part of your former graduate student, I'm rather a former undergrad student of you, maybe. I don't know if this.
What were you for?
I stayed. I visited. Well, I never know with the US, but I visited you 10 years ago in 2004, 2005, just before starting the PhD in France. So I don't know if I was grad or not grad. But anyway, so I came there with two objectives. The first one was to learn SLE with you. The second one was to be a bit more fluent in English. So I guess I achieved at least the first of these two objectives thanks to you. And I also met my wife that year in Ithaca. So for all these reasons, this was very productive here. Okay, so today I will wait. This is reversed. Okay, I don't know, this is reversed. So I will talk about a joint talk with Jean-Christophe Morat, who is also it's a work in progress rather, who is also at Lyon. And the focus of this talk will be to go to review one of your papers, a joint paper with Oded and Venlin about the one-arm exponent in critical 2D percolation. So the outline of the talk is going to be quite simple. I'm going first to focus on the one-arm exponent. Then I will talk a little bit about links between these critical exponents and how to get these exponents out of PDEs. And then I will focus on the backbone exponent. So in this paper here, it ends with an informal appendix on how to prove the existence of a backbone exponent. And with Jean-Christophe Morat, very informal appendix, we found some interesting mathematical issues there, issues that I don't know if you were aware of, we'll see, but there are nice mathematical issues raised by this appendix, and this talk is there to show what these are and to try to discuss this, and I think these issues do shed some light on why the backbone exponent stands out of the other critical exponents. Okay, so this is not meant as a poison gift, but rather to try to highlight ideas that were in this, important ideas that were in this paper. Okay, so let me define the three arms exponents that I will focus on. The first one is you take a critical percolation in the plane, and I will need to take the only one for which you have a scaling limit, so the usual one, side percolation on the triangular grid. And you may look at the probability that one point, the origin, is connected at distance r through an open path. So by Rousseau-Semmelweis, this decays to 0, and you can show that this decays in a polynomial manner. The fact that there exists an exponent is very non-trivial, and for example on Z2 it's not even known that there is an exponent there. The second event we will look at, so my picture is really bad because we don't see this arm. So it's a polychromatic 2-arm with one open. What?
There is a second arm there.
Ah, you have good eyes. So this arm is an open arm to distance r, and this, if you don't see, is a closed arm to distance r. And the probability of this decays, of course, faster than this one. It's harder to achieve these two arms, and there is also an exponent, which is the polychromatic 2-arm exponent. And the third event on which I will focus more is the monochromatic 2-arm event, where you want that both paths are disjoint and both open and lead you to distance r. And if you've never seen these things, you might naively think that these two exponents are going to be the same by some kind of color switching argument, but this is not the case. And I'll get back to this later. Okay, so in general, you expect polynomial decays. It's only known to be the case on the triangular lattice. There it's known to be 5/48, the alpha 1 exponent, and it's this theorem by Lolo, Schramm, and Werner, the paper that I just showed before. The two-arm exponent, I didn't exactly locate the difference. I guess it's a mix of Lolo, Schramm, and Werner works and Smirnov and Werner. In this paper, they focus more on the four-arm exponent, which is harder, and the two-arm is a little bit in between. And finally, the backbone exponent, I spent quite a lot of time on this. So, so to start with, let me try to help you to picture what could be the backbone of a percolation cluster. One way to picture what this is, if you know the incipient infinite cluster of Keston, which is the following: you kind of condition the origin to be connected to infinity at the critical point. The backbone of this incipient infinite cluster would be the set of all the points that can be connected to 0 and to infinity by two disjoint open paths. So another way to picture the backbone in a finite setting is to take a large R by R box and to take, for example, assume there is an open cluster from left to right. What would be the backbone? A way to define it would be to remove a lot of the dust and to keep only the points in this picture that are connected to the left and to the right using two disjoint open paths. And if you do this, we're going to remove all these clusters that are attached, that are fjords in this picture, and you'll get the backbone. So this is, of course, a special designed cluster for Greg. So the backbone is something that is much thinner. So the exponent is something which is larger because it's the Hausdorff dimension of this is going to be smaller than the Hausdorff dimension of the cluster. And if you want to study heat diffusion on a critical cluster or things like that, study electrical networks point of view on this, knowing the size of the backbone will be something that will be relevant in your study. It won't be enough because you'll have to understand the geometry of this backbone, but first you might want to know what is the size of this. Okay, so let me start very smoothly with some prehistory. Not that you are prehistorical, but prehistory of the computation of the critical exponent. So for critical percolation, as I already said, even the existence of these numbers, alpha 1, alpha 2, and so on, this is not something that comes from free, not at all. And on D2, even the one-arm exponent, we don't know. So in Lolo, Schramm, and Werner, they are the first computed critical exponents for Brownian motions, and these were actually known to exist by works of Greg and Christophe at the end of the 80s. And there, in some sense, the reasons they can prove existence of a critical exponent is that they know that random walk converges to a nice continuum object, which is the Brownian motion. And in the percolation case, unless you have the SLE6 or things like that, you don't have a candidate for the limiting things, and it's not so clear how to get existence of critical exponents. Okay, so this was the prehistory in a way. So let's move to the history. So what I would like to spend some time on is to tell you how did Greg, Oden, and Vedlin, how did they extract this 5/48 for the one-arm exponent. So their idea is as follows. They pick so there is one step that I won't explain in details, which is that you can think only at the continuum. So this is a not so hard step for the one-arm event. This is getting harder for the two-arm and the four-arm events because you need to prove separation of arms and things like that. But for the one-arm case, going from the discrete to the continuous is kind of okay. And what we want to know is what is the probability that at the scaling limit you will have a connection between a little disk of radius r here and the disk of radius 1. If you can find how this decays as r goes to 0 at the continuum level, then you are fine. You get your number 5/48. So what do? They fix an angle theta here between 0 and 2 pi, and they consider the continuum object here, which is measurable with respect to SLE6 somehow, this continuum object of all the points in this unique disk that are connected to this arc from 1 to E of I theta. And the quantity that we would like to understand is the the distance, the metric distance between this blue set and the origin. And more precisely, what is the probability that this blue set comes at distance less than little r from the origin. And now there is a usual trick which is very useful with SLEs, that by Cueb's theorem, this metric distance is up to a fixed constant for the same as the conformal radius of this blue picture seen from the origin. So if we are okay to lose constants, they don't matter in these exponents. So what you can look at is instead this probability that the conformal radius of this blue picture, the complement of this blue picture, this conformal radius gets smaller than exponential minus t. The exponential scale is the natural scale in this setting. And if you can compute, if you can understand what this quantity is, then you might get eventually this exponent 5/48. So the claim, the proposition that they prove is that this function here satisfies a nice PDE with some boundary conditions that are the following ones. You initialize your PDE at 1 when t equals 0. So this is natural because the conformal radius is always smaller than 1. So at t equals 0, nothing happens. And then it evolves like that. And you're equal to 0 when theta equals 0, because if theta equals 0, there is nothing connected to just a point at the continuous limit. And there are Neumann boundary conditions at theta equals 2 pi. Now, I won't give much details on this part. So let me very quickly tell you how to prove such a claim. What you do is you want to understand this h theta t function, this probability that this conformal radius is small. And what you have at your disposal is this SLE process. You can try to explore a little bit of the continuum percolation that you have here using an SLE, and this will tell you if you are in a better shape, if the blue arc is going to get larger or smaller from the harmonic measure point of view. So say this is a little portion of your SLE6 starting from 1. The conformal radius is a quantity that is additive under conformal maps. So if you use the Loevner equation, and here I made the point 1 stable, but it's not needed. Then if the SLE did this, on the picture it's clear that the harmonic measure of the blue is going to be a little bit harder. And now the angle is going to be theta u, where u is the capacity of this set, of this set here. And what's natural to do is to see what we gain with this little exploration of the SLE6. And if nothing bad happened, like a circuit around the origin that would kill any open path from the origin to the initial arc here, then what you end up with is this quantity. You only have to achieve that the conformal radius of the new angle theta u is going to be less than not exponential minus t, because you did gain some conformal radius. The only thing that is remaining is exponential u minus t. So this is only this would require more justification because of this possible stopping time in between that could happen. But modulo this, you get this equality here, and this tells you that the process u gives h of theta u minus t. This is a martingale, and you can prove by other means that h is something that is C2, that is reasonably smooth. And if you know how the angle is evolving in time, then this will give you your PDE in the bulk.
No, the next line.
I think there it's u minus t, because it's exponential. In the definition, it's exponential minus the time you're looking at.
Let's not worry about it.
What?
Let's not worry about it.
Yeah. Okay. So then it's possible using the SLE technology to write down an SDE for the evolution of this angle. And if you plug this SDE using Ito's formula, this gives you this constraint on the function h that we want to compute. And this explains at least this PDE here in the bulk. Then you need to struggle a little bit more to check that the boundary conditions are indeed the one that I wrote. The Dirichlet one is easy. For the Neumann boundary condition, you need to rely on Russo-Seymour-Welch and easier critical exponent that can be computed on the upper half plane. And you can identify that indeed this PDE has this boundary condition, and now there is a unique solution and you can work with it. So what they prove is that they identify this critical exponent, its existence and its value, as the leading eigenvalue of a differential operator on the interval, which is this one. And they compute that this value is 548. So there is some tricky or elaborate use of the maximum principle due to the presence of this Neumann boundary condition to show that indeed the value they want to look at is in between the behavior of the first eigenfunction. Sits in between. Okay, so so what I want to point out is that this historical approach in this paper is, as they write in the paper, of purely PDE nature. And one might want to try another approach, which in the end is very similar, but I don't know exactly how close this is. So what you may want to do is to forget for a while this h theta t function and just to explore the exploration configuration. And what you do is you let your SLE6 go towards the origin. So this is going to be a radial SLE6. And you follow what the harmonic measure of the blue arc is along your conformal map. So in this picture, it's supposed to go high all the way to 2 pi and then kind of reflect with Neumann boundary conditions there and go down. So in the bulk, as I said, it's easy to identify that the scaling limit of this exploration procedure is this Bessel-looking diffusion in the interval. But what you would really want to compute is the probability that your process does not die by the time t, meaning that this process doesn't go to theta equals 0 within a time t. This will mean that you will reach reduced exponential minus t, and you will still have a chance to have an open arm to distance 1. And if you do that, what you want to analyze is this quantity. And if you prove, so it will be a different technical kind of proof than the proof that characterized Neumann boundary condition directly on the PDE. If you prove that this stochastic process is indeed this Bessel that is reflected the right way on theta equals 2 pi, then you get this PDE in a very related but slightly different perspective, and I'll get back to this later. So this way you can compute that this probability satisfies the same PDE as the one I wrote before, with the same initialization, and so these two things are just the same object in the end. But I think the technicality is a little bit different. Here you work on the stochastic process and how it behaves near the boundary, and in the other case you work with the PDE itself. So let me quickly say a few words about the polychromatic.
I'm not understanding. Are you making a distinction between how to justify the discrete to the continuous, or discussing only on the continuous level?
No, I put the discrete also in this picture.
Okay,
so for example, okay, I guess the technicalities are very close. We'll see this more in perspective later, but if you want to prove that the evolution of the angle with the scaling limit of the evolution of the angle for the discrete process is this with Neumann boundary conditions.
yeah. So okay, so it's in the justification.
Yes, I'm not sure this is really written or done. This is
okay.
Yeah, that's what I mean.
That's good.
So the second event we may want to look at is the polychromatic two-arm event, the one where we didn't see the second color. And there you can also prove that the two-arm exponent is the leading eigenvalue of the same differential operator. So the same PDE pops up. But this time the boundary conditions are different. They are Dirichlet on both sides of the interval. And in some sense, if you want to justify this, things are going to be slightly easier because if you think of the second approach, for example, what you want is that your exploration process will not disconnect the initial blue arc and will not disconnect the initial red arc. So there you know that the scanning limit of this exploration procedure is this SD in the bulk, and there are no problems near the boundary. So there you really want to understand the probability that this diffusion will live for a very long time, and this is related to this PD here, but with different boundary conditions. So now let's move to the third exponent in this story. So the first warm-up that I would want to make is, at least to me, when I started looking at that, it was not clear at all why the SL6 would be of much help here. Why? Because you have these two-arm monochromatic event. SL6 has an open arm on one side and a closed arm on the other side, and how come you're going to check if this event holds or not? This is not so clear. And there is a very creative idea in this appendix that before reading this I didn't know what to do. I tried myself to see, but I had to read and see this idea. So what they do is they have the idea to follow 3 angles instead of 2. So far this is quite natural, but then they consider the following event, and that's where it's quite creative, because you can think of many events, and most of them they're not going to work at all. But this one was the good choice. So what do you do with these 3 angles? So this angle is the closed vertices, the white hexagons. So this is the black vertices, and there is a third angle which is a sort of gray side. And the sets that you're looking at, a little bit like in the one-arm case, you look at the set of all points at the continuum limit that have 2 arms connected to this gray line. And the trick is, and it's important, you want to have 2 disjoint arms that go to this gray line, but they may use, if you want, they may use the black side of this disk. So for example, this point here that I've drawn here belongs to the set I want to consider. So what I would have done more naively is I would have looked at the set of points that would have 2 monochromatic arms to the gray arc, and that's it. So there is this flexibility that you can use this extra angle beta. And now what you want to know is how large this set is, how this set is likely to go very close to the origin. So exactly as before, you want to look at the Euclidean distance between this blue set here, which is different, and the origin 0. And by same Kirby distortion, you're going to look at this function here. So this function now has 2 angles, this one and this one. The third one is just 2 pi minus the sum. And you want the probability that the conformal radius of this blue thing, this complicated blue thing, gets smaller than exponential minus t. Okay, so stop me if this is not good, because I'm going to keep this for a while. So let's try to analyze what this function does. So I recall the definition here. And so the claim is that this function is going to satisfy the following parabolic PDE. So things are getting a little bit more nasty with this backbone exponent. So it's going to satisfy that, and I'm going to justify in a minute how you do this with the following boundary conditions. So it's going to be Neumann there. It's going to be Dirichlet on this side. And there is a kind of strange boundary condition which is constant in time. So we'll see what this means later. But at least that's what the function satisfies. So let me try to say a few words. Are you fine with the 1230? So as before, you can run a little bit of an SLE process and condition with respect to it. So probability that R alpha beta t gets smaller than exponential minus t. Sorry. Knowing what happened with your small exploration path up to time u. And a little bit like before, this is going to be roughly the expectation, the probability and this time we will have t minus u. So as before you have a martingale, now you need to follow the evolution of two angles, and they follow the same SDEs as before. So you know that d alpha u equals square root of 6 dBu plus cotangent theta u t alpha u du, and the other one has the same driving ground motion with a negative sign plus cotangent beta u du. And playing with Ito's formula gives you exactly this PD defined on the triangle. And then you can try to see where these boundary conditions come from. The Neumann boundary conditions can be proved a bit like in the one-arm case. It also arises from Rousseau-Seymour-Welch at small scales. The constant boundary condition, this one is more subtle. So it's just the fact that if you keep the closed angle fixed, the events that I have drawn before, so I have my gamma and my beta angle, it doesn't depend on the location of this point here. And the reason is that I can use this black arm, so the location of this point is not really important. And because of this, I must have constant value, which may depend on t, but constant value near this boundary here. Okay, so now that you have that, the claim is that the monochromatic two-arm exponent is the leading eigenvalue of this differential operator on the triangle with this set of boundary conditions. I forgot to, so the Dirichlet also, and this is important, Dirichlet also includes these two corners. And this is supposed to represent the bias, the vector field in this triangle. So it gets a push when it gets here, a push when it gets here, and there are big pushes there. So let me try a meta statement with now that we've seen all these exponents. In general, all examples of non-critical exponents, at least in percolation, they are obtained in some ways as leading eigenvalues of some differential operators. So I just gave 3 examples, but even the plane exponents, the alpha 4 exponent, for example, in some way, the derivative exponents, they also come out of leading eigenvalues of differential operators. Brownian intersection exponents, also from the work of Lolo, Schramm, and Werner, it's the same story. There are some counterexamples, though. For example, the classical exponents that are also known for Z2. You could cook up, of course, a differential operator, but they don't really come out this way. This is simpler. For the plane exponents, it's a bit easier too. It's a bit different. And the last example that I can give is they have a paper to find critical exponent by analytic continuation of the other ones that they know. So there, I'm not sure we can say that this is still a leading eigenvalue of a differential operator. So let's keep this meta statement in mind. So as I did with the one-arm exponent, so I said that you have maybe 2 ways of understanding how to get the critical exponent. Either you think purely in terms of PDEs, or you try to study the associated stochastic process, and this is something that we all like to do, I guess, to see what is the stochastic process associated to the PD that you want to understand. So let's try to to understand what's going on here with the stochastic process. So this term here is telling you that you have a Brownian diffusion term only on the diagonal. So the PD is parabolic, it's not elliptic. You don't. So as I will mention later, the Ormander theorem can be applied here because the vector field is sufficiently is not constant enough. It varies enough. So there are some continuity estimates, but think of your process as something that fluctuates along the diagonal and follows this deterministic drift, rather complicated drift on this triangle. And how to interpret the constant condition on this left side of the triangle? One way to interpret this is each time you bump onto the left side, think of your stochastic process as starting over from the origin. And in fact, I will say a few words on this. This is exactly what you want to do on the discrete picture if you want to explore the monochromatic two-arm event. And that's where I find this strategy very creative. So maybe I should do it now. And it's also Dirichlet on the top and on the two corners. So this stochastic side of the story tells you gives you a nice algorithm to detect the monochromatic two-arm event. So let's imagine that my disk is this triangle. This would be the gray side. This would be the black one, and this would be the closed side. And I want to know if this little radius here has two disjunct monochromatic arms that are connected to this guy, possibly using this black arc here. So what do we do? Well, the only thing we can do is, it's natural to start an SLE from this corner because this is going to match with these boundary conditions here. There is no point to start something gray that I don't really know what it is from here. So let's start an SLE, and it's going to do something like that. And let's imagine it does this. So far what it did is that it observed that there is a black side here and a dotted side here. And the probability that you have two monochromatic arms by conformal invariance, you can map this back to the triangle and see how the angles evolve, as we did before. But on the discrete picture, what happens if you go here? Once you touch this side, you don't have a dotted color anymore visible from here. And the algorithm that this is suggesting is that you will flip all this black color into gray. And let's see if this is working. Now, if we think of this function, what we want to do is we just want to send two monochromatic arms wherever we want. And if you look at what's going on, this is fine because for whatever configuration, for example that, this arm is going to use this black arm and this one is going to do all the way around to this, and this is working. So in some sense, this flipping of colors, this algorithm that flips along the way when you disconnect the dotted arc, this is something that is stable along the way, and eventually if you're still alive, if you don't find loops, you will know that you have a monochromatic two-arm event. So really this stochastic side of the story that I guess they had in mind in the appendix really tells you how to do algorithmic-wise to observe whether you have a monochromatic two arms or not. And so what we did with Jean-Christophe is we kind of looked at this story, and we've seen some troubles thinking of the stochastic approach. And I'll try to make a list of these few issues that are raised. So the first one is not so bad, but still deserves some answers. So if you study this stochastic process, it's easy to see that it will never reach the red line, the diagonal. Almost surely this stochastic process will just never go here. It might go there or there, but it will never reach the open diagonal here. So once you see that, you may wonder, why do we put Dirichlet boundary conditions there? Is it needed? What exactly is the meaning from the stochastic process point of view of this Dirichlet boundary condition that is there? The second problem, so I'm not 100% sure this is a big problem, but at least we didn't really figure this out. So the process that I am looking at here, which follows from this generator, this is not something that is reversible in any way. This is really intrinsically non-reversible. You cannot find a measure, natural measure for which this will turn into something reversible. And so this differential operator, this is really non-self-adjoint. And so just the existence itself of a positive eigenfunction, maybe there is a theorem that we don't know, that's possible, but at least it doesn't come from free. I see some experts that I can talk with. Okay, so maybe, but at least there is some substantial theory to check there, and there are some kind of nasty boundary conditions, so something needs to be said, and I'll say a few more words on this. A third issue, which I wrote as facultative, because as I pointed out, you can make a purely PDE proof potentially. So as in the one-on case, it's not clear you need to prove the convergence of the stochastic process. But if we might need to rely on this stochastic process, can you prove that it has a scaling limit? And the third issue that we struggled a little bit with is the following. So assume the process is well defined. As with the one-arm case, what you want to look at is the probability that this stochastic process survives up to time t. And exactly as before, this is going to satisfy the same PDE as the one I had here, with the same initialization. So this G hat is going to be the same as the G. The probability that the process in this triangle survives up to time t satisfies the PDE that is here. Okay, and this is a problem. Why? Because there are two strategies for your process to remain alive. Either it's going to spend some time here and bump into the left corner and arise from zero again and bump a few times and try to keep being alive this way. Or, so at least two strategies, you can imagine many other things, but another natural strategy would be to say, okay, I don't really care about this left boundary, and I will just let me flow closer and closer to the diagonal that I will never touch, but closer and closer. And this is a sensible way to remain alive. And it's easy to see that the second strategy corresponds to keeping alpha and beta both alive. And this is exactly what we studied before, the polychromatic two-arm event. So this strategy of being alive up to time t, this is at least larger than the probability that the polychromatic two-arm event holds. And this is an issue because there is a theorem by Vincent and Pierre, which states that that it's more likely to have a polychromatic two-arm event than having a monochromatic two-arm event. And here I'm using really the full strength of their results, because Reimer tells you, or things like Reimer tells you that there is a larger or equal, but if you know that it is strict, it means that it is impossible that both functions satisfy to the same PD. So what happens here? So where does this issue 4 come from? So in the one-arm case, when you want to make this step rigorous, you need to introduce a stopping time, because maybe something wrong happened, you found a loop or something, and you have an equality like that, which tells you that you have a martingale and that you can use Ito's formula. In this monochromatic two-arm case, it turns out that this does not hold anymore, so there is something more subtle going on that can be explained. And therefore, the heuristic that I wrote there is wrong. There is something more subtle going on. And the only thing that you obtain is that this function that you would like to compute is only a sub-solution of the PD. And because of that, it starts being less clear how to extract the exponent out of this technology. So, so now if you still want to get the exponent, how to proceed? So there is a first way to proceed, which is to just ignore all that, all what I said. And in Beffara and Nolin, in Vincent and Pierre work, there is a second proof of existence of monochromatic arm exponent, where the main tool is to say that it's measurable with respect to the scaling limit of the full percolation process. And we have at least two full scaling limits of percolation, the one by Kamiya-Newman and the one by Schramm and Smirnov. So use either of these and you see if the monochromatic in this continuum limit holds or not, and you can prove that there exists a critical exponent. So in some sense, it's fine that there are mathematical issues there. You can just forget and use this point of view. But what you need in this case is you need the full scaling limit. You need something that maybe is a little bit too strong just to get the exponent. And maybe having a direct SLE6 or a PD approach is still desirable.
But approach A is just for existence of exponent, or for actually?
So this approach is for the existence of the exponent.
Not for actually.
No, in some sense, all this approach also, because we don't compute the exponent.
Okay,
We give a characterization, but
Okay.
but yes, this proof here is you can extract it out of the full scaling limit, and a little bit like in your proofs for the Brownian motion, it means that there exists an exponent. So we'll try something anyway. So let's try to do a direct PDE proof, like in the one-arm case. Let's see what's going on. So this is still in progress. I don't know if we will achieve this part, but this is interesting anyway. I'll say a few words. And another possible thing is to try this second approach that looked very, very similar in the one-arm case, but in the monochromatic two-arm case, this seems to be a little bit easier. So let me investigate first the PDE approach. So I recall to you the issues. The operator is not self-adjoint, so the existence of these positive eigenfunctions is not so clear. Maybe there is a theorem we don't know. That's quite likely. But in any case, even if there is such a theorem, you don't have the nice Hilbertian structure that you have with the previous differential operators that we had. There is no orthogonal basis of L2 of the function that will. So in any case, the setup is going to be more nasty. And the proofs that the first eigenfunction will be the leading order is not going to be as easy as in the other case. And already in the one-arm event, as I told you, there is some rather tricky use of the maximum principle. So there it's going to be a lot worse, I suspect. So furthermore, it's not clear which PDE to play with, because the quantity that we want to look at, this one, does not satisfy the PDE. So you need to think a little bit on this side. And the boundary conditions, at least to me, they're very frightening. So there were talks yesterday with reflecting random walk and see when Neumann boundary conditions is still there or not. Here there is something a little bit of this flavor. So to give a little bit of the issues, let me just consider a very simple toy model. In the true stochastic process we want to look at, there is this behavior that it tends to go towards the diagonal, and in some sense the diagonal is at infinity, because we never reach the diagonal. So let's take a very simple example where we have this tendency to go to infinity, but what we would really want to is that the process is going back near the origin. So this would be this simple PDE here with Neumann boundary condition at 0. So we just look at a process that has a constant drift towards infinity, and we reflect it with Neumann. And there, if you analyze this easy toy model, you can find several positive eigenfunctions that are natural. And probably among all of these, the most natural one is this one, which has Neumann boundary condition at 0 and is in some sense Dirichlet at infinity. It goes to 0 at infinity. And probably what we want to find here is exactly this, something that is Dirichlet there, Neumann here, constant here, which I'm not yet sure exactly what this is, and tends to 0 near the diagonal. And probably if we want to define a proper generator, a proper domain for this operator, we will have to add this condition that it has to go to 0. But this has to be done with some care, because if you don't converge quickly enough to 0, you can see that the PT of F is not going to give you the leading order of the monochromatic to arm event. So there is a subtle condition on how fast do you need to converge towards the diagonal. Okay, so even in the very simple toy model, there you can prove that this eigenfunction gives you the right eigenvalue to be back at 0. There things are simple. But even to write things properly with having in mind the more complicated figure here, I'm not so sure that it's very clear. So with this problem of lack of Hilbertian structure and things like that, what are the possible tools? So here in the Bereztiki family, I'm going to pick the father, which is a bit unusual in this crowd. So for example, in this paper, we found some sentences that seemed related to what is going on here. So it's related to the technology of viscosity solutions. And in this paper by Bereztiki, Capuzzo, Dolcetta, Porretta, and Rossi, which is not a whole paper, they claim that viscosity solutions that are usually designed for nonlinear PDEs and things like that can be useful even when we deal with a linear PDE, as we do here, if the boundary conditions are kind of bad, and if for example it's not elliptic or things like that. So I'm not going to read the full sentence, but there they say that even in the linear case, this framework of viscosity solutions may be the right one. And then, so where is it? So finding positive super solutions, a little bit like what we need here, is a key part of their theorem. And their sentences seem to say that things are subtle there, and we need to investigate more this thing. So we didn't find purely PDE proof at this moment. So let's go to the other side, which for the one-arm case, some of you might have thought this is just the same. But at least here, I think it's more comfortable. So this goes into 3 steps. First, make sure that you indeed have a well-defined stochastic process at the scaling limit of this discrete exploration procedure. Then obtain a candidate for the exponent we want to look, the monochromatic 2-arm, and this exponent will get it out of a rather classical subadditivity property. And the last step is to say that what comes out of the subadditivity indeed matches with the geometric exponent. So the step 1, I'm not going to say much about it, but what's important when you want to prove convergence of geometric events for the discrete percolation and their continuous limits, you don't want to have too many stopping times and things like that. And in some sense, what's going on here is the following. There are 2 coupled SDEs. One is the angle of the dotted line, which is something like that. So it has a Neumann boundary condition at 0, and it's Dirichlet at the top. And the other one, what it's doing is the following. It's also the same kind of SDE that I wrote there, but with a minus sign. So I don't know. But when this is reaching 0, this starts over from 0, and then something a little bit nasty happens, and then it starts over like that. So in some sense, defining this process doesn't look very frightening. It's a little bit like starting infinitely many Bessel process from the timeline, which usually we see many flows that start continuously many Bessel processes from the y-axis. There we need rather this part here, which needs some justification. And to prove the convergence, we proceed as usual with approximation. So something like every time you get back to this point, instead of going back to 0, go back to some point delta delta and try to see if things do converge. And there are many approximations that are a bit nasty because things don't couple in the end, but there is one approximation mechanism that is very nice that make this picture very stable. I can tell you more if you're interested. And this approximation mechanism is also very nice on the discrete side of the picture. So you can make the whole convergence together. And you get a stochastic process xt. Saying that this stochastic process does match with the boundary conditions, this is another story, and that's probably the case, but I'm not 100% sure. The second step is to find the subadditivity somewhere in this story. So what you would want to say is that this stochastic process has this kind of subadditive property. But things are quite degenerate here. You have this non-ellipticity in the triangle. So you may use Hermandel's theorem, but one can find easier ways to achieve this subadditivity here by looking at such functions. So there we gain some continuity by looking at the probability that the process is back at 0 between time t and t plus delta. And what's easy to see is that if you have time t plus delta, and t plus s plus delta, and t plus s plus 2 delta, it's straightforward to notice the following subadditivity property, multiplicative property. But there is this little shift in the cutoff that you've chosen, and a little lemma gives you this slightly better shaped subadditive property, which is not the standard one, but from this it's easy to get the existence of an exponent. So this part is quite classical. You need to deal a little bit with the fact that your process is very degenerate, but you can still cook up rather quickly a subadditive argument. But once you have this exponent, you need to check, you need to identify that this is the correct one. And so let's define AT to be the backbone event, to be this event that from exponential minus t you get two arms connected to distance 1. Our goal is to prove that indeed this event is decaying like exponential minus the exponent we just found. So the lower bound is very easy. Why? Because one strategy to achieve the monochromatic event is to be back at the origin at time t. And what this means is that the gray angle is huge. And if at time t minus 10 you're back at the origin, you know that you have only 10 scales to go to 0. So you have a picture like that. At 10 minus 10 you have gray everywhere. And the little disk you want it to go, it has changed a little bit by the conformal map, but this is something of size roughly 1/10 or exponential minus 10 rather. And by Russo-Seymour-Welch, you know that there is a positive probability to make your event work. So the lower bound is easy. The upper bound, it's not going to be awful, but if you do it wrong, this is terrible. The upper bound, the most natural thing is to say, okay, I'm going to let the stochastic process evolve, and I'm going to decompose according to where it lands at time t. How far does it land from the diagonal? And if you do that, this is almost impossible to analyze, because if you are on this part of the triangle, then you can understand what it means geometrically. But if you are on the same level line but very close to the corner, something very different is going to happen. So the right decomposition in this setting would be to decompose according to different type of level lines that would be shaped more like that. And I think these level lines would be the level lines of the eigenfunction that we are looking at, but we don't know what it is. So this way it's a bit frightening, but there is another way of decomposing things, which is to decompose according to the last time you've been back at the origin. So this is not a stopping time, so you need to be a little bit careful. But decomposing this way, you see that this is roughly, up to the fact that this is not a stopping time, the probability that at t minus k you've been back at the origin modulo unit constant of time, and the probability that from this time you will never be back at the origin. And this, you can interpret this geometrically as creating 3 polychromatic arms events. So in this sum, you bound this sum by this times something with an exponent that is geometric and that you know. And you conclude by a case study thing that if lambda, that you didn't yet relate with anything geometric, was larger than alpha 3, then you would find that in fact this probability would exactly be like the polychromatic 3 arm event, and this is not possible because this is much larger by FKG. And therefore the exponent has to be smaller, and once you know that it is smaller than alpha 3, by this reasoning here, you know that this is equal. So this ends the proof. Let me, in 3 minutes, give you a few perspectives. So the first one is that one of the interests to try to have a proper PD approach, or to have is to do numerics, to do simulations. Because one way to find what this value is to run many percolation samples and to see on these random samples of percolation what could be the alpha 2 prime. Another way would be to simulate the PD, but you need to know what you need to simulate. Maybe in the end it's much better to run the random picture. I have no clue. But usually the PD approach is kind of doing everything simultaneously. Usually this is a good way to handle things. Another thing we're looking at is that this approach, I'm pretty sure is giving the backbone exponent for all the other values of kappa. What's harder is to say that they are related to the actual discrete models. So for example, for kappa equals 16 over 3, for the FK case, this should be feasible, but this is going to be harder. But at least getting an exponent with this subadditivity technique, this is going to work, and I'll say just a few words on that. And the last thing is that we were quite amazed by this very nice algorithm with triangles and the right event and how to discover this monochromatic 2 arms. And the natural question is to ask, can you find the monochromatic 3 arm events with such type of exploration procedure? And in some sense, in this idea, you follow several angles and you let the SLE grow. And there are not so much flexibility. You can recolor things. You can make your SLE change of targets. You have some group structure that you can imagine on these procedures, and you can list all the group that preserves a geometrical event that is observed. Then you can list and try to see if there is one of them that could lead to the monochromatic 3 arms event. I'm not completely sure of the answer yet because we didn't do the listing properly, but I think it does not exist. So if you want the 3 monochromatic arm events, things are even more nasty. You kind of need to go through the full scaling limited things. And surprisingly, axiomatizing this, we found that you can find the 4-arm critical exponent with a PD very nasty on the 3-dimensional triangle, but in a different spirit of what is done classically, because the things are explored simultaneously towards 0 and not first a 2-arm and then a 2-arm in the upper half plane. So there is something maybe to be looked at here. So I just, with time I don't explain to you for kappa different from 6, there is an operator on the triangle that will give you the backbone exponent there. So fortunately it matches when kappa equals 6, that was our check. But otherwise it makes the PD more complicated because it couples even more the 2 coordinates. Still I think the proof works. And as a conclusion, so the meta statement that I wrote earlier, this has to be taken with more caution if you want to include monochromatic exponents, but it may still hold if we know what we mean by a leading eigenvalue of an operator. If these viscosity solutions or other point of views work, this would work. This can help to compute this quantity, and this sheds some new light, I hope, on why the monochromatic arm exponent is different. I'll just write this conjecture by Vincent and Pierre that it seems from the simulation that alpha 2 prime is just the sum of these two. So I thought it was a nice way to finish. And there were some discussions yesterday on how some of the cakes we've seen were done with Greg. So this is a purely cake generator on the web, as we discussed. Okay, thank you.
Thank you. Yeah.
Let me first make a comment that when we wrote those papers, we didn't know as much PDEs as turns, and that's not how at least how I teach people how to find these things now. It's much more probabilistic. When you have the PDE, you find the invariant distribution or quasi-invariant distribution. Find a process, maybe use Kirsanov theorem to look at a different process, get close to the invariant distribution, take estimates. Sometimes for a problem like this, I haven't revisited this problem. One need you may have to invoke Hormander to show that you actually go to the invariant distribution, but you don't need things to be necessarily self-adjoint or anything for this to be true. It's useful if you happen to know what the distribution is.
Yeah, that's a bit what happens here, that eventually I'm not going through the self-adjoint or operator point of view because I don't know.
It's finding what the invariant or quasi-invariant distribution is.
Yes, but here the quasi-invariant is not clear because the mass is going really towards the diagonal. So
then you have to find a rescaled thing, change coordinates. I don't know what can be done in this case. Okay, I haven't revisited this case. But yours, sir.
Yeah, I mean, if I remember correctly, I mean, somehow there's this. You don't really need to control the entire process in some sense because somehow, I mean, each time you see an excursion of S76 away from the boundary somehow, then you can re-initialize because so somehow you just need the law of the jumps. A little bit like when you explore CL4 or something, that when you get on the
so there would be the construction there that you...
Yeah, so the issue I think you have with the alpha 3 and the thing where you're getting close to the boundary has to do with the fact that it may happen that you have a very, very long excursion of S76 that creates basically the two macroscopic arms. But I think if you just, not stop when you reach distance L, but you just look at the law of the entire until you come back sort of by this chunk on the excursion. Maybe you don't have this problem with the alpha 3 boundary thing.
Well, the issue to me is really that you cannot interpret things as probability of surviving. So even probabilistic-wise.
Okay, we can. I mean, the thing is that if you get very close there, then at some point you're you have the two arms, and then you still have it's not the right event, so you're going to be penalized by something.
True. And on the PD side, this is saying that the Dirichlet needs to be there, and even with a certain decay near the diagonal.
I think we should postpone the next question to the coffee break otherwise. Thanks again.